So in this talk, I've been basically asked to talk about the Higgs particle, and it's a fairly rare occasion that I can talk about something which has been announced just 16 days ago on July 4th. Of course, that wasn't the first time we all heard about it, but at some level, this is the official announcement, and it was a historic day, July 4th. And my job is to explain to you in some perspective what is all this about. And maybe this means I'll have to spend about half my talk giving you the perspective. What do we understand about particle physics? What is the subject? Why do we do it? I think will become obvious. What do we know? This is very important because sometimes the press tends to highlight only those things we don't know under the banner scientists don't know everything, which is true. But in fact, scientists know quite a lot about particles, and I think I should make sure that I convey that to you in a somewhat non-technical elementary form. If something I'm saying is not clear and you need clarification at that moment, please don't hesitate to interrupt me, and otherwise at the end of the talk, you will have time for questions. So let me get on with it. So let me start by saying I thought of many alternative titles for this talk, and here was one of them, Higgs, the 13th boson. So it sort of has appeared in our picture of elementary particles as the 13th member of the family of bosons. Whether that member is Jesus or Judas, that I will leave to you to decide. Another possible title was Higgs soup, because as we'll see, its main job is to form a soup. And there's the soup. I think this is a tomato soup, not a Higgs soup. But anyway, now you see some W particles propagating through that soup, and as we'll explain later in the talk, this has a very important effect on the way particles behave. And of course, it has entered popular culture, and so there's even a wonderful song which you can see, it's called Higgs Don't Lie. So now let me start with a little bit of history. So the history is, as always, it's one single question for particle physicists. We are very boring people. We keep asking the same question over and over again. What is matter made up of? Okay. Now it's a very ancient question. It's not new. And both the ancient Greeks as well as in Vedic civilization as well as or Indus Valley civilization perhaps, no, maybe not, but certainly in Vedic times, people had the idea of reducing all phenomena to some simple building blocks, and earth, air, fire, water, and so on were proposed as the building blocks. But of course, now we know that while this is a nice idea, it's not actually correct, and it doesn't actually have any meaning or any implication. It may be a way to think, but it's not a way to actually do anything. But it was a good start. And the next start, which was really a lot better, was to reduce all of matter to 100 plus elements. And as you know, elements combined with each elements are basically atoms. They combine to form molecules, and molecules are the things we use and we eat, for example, in the case of the last one, sodium chloride. And the special properties of them, which make them, for example, edible or not edible, depend on the way the molecules bind, atoms bind to form the molecules. And the whole thing is summarized in a table called the periodic table. And here you see basically all the elements, and at some stage it starts to run out around 110 or something. That's because at that stage the elements start to be very, very unstable. And that's an interesting issue for experts, but most of you will only encounter the elements in the first 2 or 3 rows. But at least this sorts out the mess of what all of matter is made of. It's made of elements. Now that would be great, and it would have been the end of the story very long ago if only the elements were actually elementary, which means made up of nothing else. Okay? But that's far from being the case. In fact, elements are made up of all kinds of stuff. So if I look inside one atom, I find all kinds of things happening. So here's a lithium atom. Okay? It has 3 protons, 4 neutrons. The protons are red, the neutrons are blue. They are all bound in a lump at the center of the atom, and then it has 3 electrons that are sort of, roughly speaking, orbiting this nucleus. Okay? So that's the structure. So there are actually 4 plus 3 plus 3 more, at least 10 particles involved in just making lithium, and that's one of the simplest atoms. If you go to heavy elements, then you can have literally 100 or 200 different objects making up the atom. So we should focus on those objects and not on the atom. If we know those objects, then hopefully we can think of binding them and making up the atom. However, protons and neutrons, those red and blue things at the center of the atom, are also not elementary. Okay? Now this realization brings us to somewhat more recent times. This fact began to become clear around the 1940s or 50s, and it became most clear in the 1960s when people found out what is inside them. So let me remind you, you might have read this or you might have heard it. The thing that's inside a proton is 3 objects called quarks. Okay? And quarks come in a variety of types. So here you see 2 labeled U and 1 labeled D. So U stands for up type quark, D stands for down type quark. These are just names. Okay? At some level we have to just make up names because these are newly discovered objects. So 2 U quarks and a D quark make up a proton. What about a neutron? Well, turns out that's 1 U quark and 2 D quarks. So that's nice. With only U and D quarks, we can make both protons and neutrons. Okay? And now finally, we have some sort of handle on what's inside the atom. What's inside the atom are U quarks and D quarks bound in this way with electrons going around. So the picture hangs together pretty well. These are the particles you find inside an atom, and they make up all of matter as we know it. And to our knowledge, electrons and U and D quarks are fundamental. That means they are not made up of anything else. Actually, a scientist will tell you that even if they are not fundamental, it doesn't matter. For practical purposes, at least at energies we can reach, it's as good as if they were fundamental. So let's just assume that. Now, I have a little movie. I don't know if it will play, but let's give it a shot. So the idea is there. So here I've given you numbers. Earlier there were no numbers. 10 to the minus 10, that is 1/10,000,000th of a meter, is the size of an atom. Okay? 1/10,000th of that is the size of the nucleus. Within the nucleus you have protons. The protons are of size 10 to the minus 15 meters, and within them you have quarks whose typical size is 10 to the minus 18 meters, and that's pretty much it. So I'm just to summarize what I've already told you. Okay. Now if these were all the elementary particles in nature, that would be great, we would be done. But in fact they are not. There are many more elementary particles in nature, and let me list some of them and tell you where they are found. So if you all look up, see anything coming through the ceiling? No. The reason you don't see it is that you are not equipped with a muon detector or a cosmic ray detector, but if you had one on your lap, it would keep going beep, beep, beep like this every few seconds, because muons and neutrinos and many other particles are streaming down on you right now. Where do they come from? Of course, from outer space. You see, all kinds of things happen in outer space. There are planets, there are stars, things collide. Whenever they emit some particle, if that particle has a long enough lifetime, it goes off streaming space, and some fraction of them will surely land on the Earth. Okay? The sun in particular is a good source of neutrinos. So these are all falling on the Earth, but they are not used to make up any atom. Okay? So we don't only focus on those particles that make up atoms, which make up matter. There are others which exist, which are created in collisions, and which are around us and which we can see and measure, and muons and neutrinos are just 2 examples. And there are still more. Ever since people started creating high energy accelerators to collide particles against each other and see what comes out, which we'll also see later in this talk, they found that sometimes new kinds of quarks come out, and sometimes new kind of other particles that are similar to electrons but much heavier also come out, and they carry names like charmed quarks and tau leptons. You don't have to remember all those names. The point though is that these are particles which are very short-lived, but they can be produced in accelerators, and we certainly know that they exist. So now you see that the set of all particles that make up our universe is growing steadily. It's not just electrons and a couple of quarks. There are more quarks, there are muons, tau leptons, neutrinos. But luckily we are sort of coming to the end. And let me just say that all the particles I've mentioned up to now have a particular quality. The quality is called having Fermi statistics, or in short we say the particle is a fermion. Okay? And I just want to mention this, but let me just tell you that all particles can be only one of two kinds, fermion or boson, and they have different characteristics, and fermions have a very special characteristic. They are extremely uncooperative creatures. Fermions do not like to be in the same state at the same time. You might imagine that each of you sitting in your chair is a fermion, because you wouldn't appreciate it if somebody else would come and same chair at the same time. Okay? You wouldn't mind if somebody sits in the same chair at a different time, okay? Or a different chair at the same time, but not in the same chair at the same time. So fermions have this uncooperative nature. They do not like to share their chair with another fermion. Okay? Now that's extremely important. It's extremely good. You might think they are selfish creatures, but you see, elementary particles are not creatures at all. They don't think what they're doing, obey the laws that are given to them. And it's very good that particles like electrons are fermions, because this is really responsible for atomic structure, for the way semiconductors behave, for anything that's called electronics. What is electronics after all? It's the complicated behavior of bunches of electrons in some system like a metal or a semiconductor or a superconductor or an insulator. In all of those cases, the single key property of the electron is that it's a fermion, and it will not be in the same state as another electron at the same time. Just to give you one example which you can easily appreciate, a complicated atom, let's say more complicated, or maybe even lithium or more complicated atoms, they have electrons moving in orbits around them, okay? But these orbits get stacked. We call them shells, okay? So some electrons are in the outer shell, some are in the inner shells. Why do the ones in the outer shell stay in the outer shell? Because if they try to come into the inner shell, the fermions which are already there will not allow them. Okay? So you see that this stacking behavior of electrons in shells of an atom is due to their fermionic nature. If they were not fermions, they would all collapse, and most of atomic structure as we know it would simply not exist at all. So all the particles I've told you about up to now, namely electrons, muons, quarks of various kinds, all of them are fermions, and their fermionic nature determines a lot about what they do. For example, how they bind is determined by their fermionic nature. One thing you may find amusing, some of you might have noticed that when I showed a proton as being made of U and D quark, I had colored the three quarks differently. I don't know if people noticed that. The reason for that different coloring was that if there was not something to distinguish the three of them, then they would all have been in the same state at the same time, and that's not allowed to fermions. The only way out was that they are actually different particles, so their color is part of the state that they are, and since they are in different color states, it's not a real color, it's not a color you can see, it's some attribute. Because those are different, it's possible for three of them to bind inside a proton, and in fact that's how this threefold color attribute was in fact discovered. Good. Now we've got a bunch of fermions, we know something about their intrinsic properties, but we haven't really seen how they interact. What is it that makes two different particles interact with each other? Okay. Now, for example, when you have an actual collision, let's say of two cars, or these days two trains, or whatever it is, when you have an actual collision, the objects which are made up of many particles, actually though you see it as a collision of two objects, really if you looked with a fine microscope, it's nothing but pairwise collisions between a particle in this object and a particle in that object. Okay. But once you reach that level, then those particles, once they are fundamental, then you have to answer the question, what is it that those two particles do? They are not lumps, they are not spheres, they are not stones. So what is it that makes them bounce? Do they actually touch each other and bounce off? What is the force between them? And at that scale, we really shouldn't talk of forces, of things touching. We should talk of things coming close, experiencing some force or some field, and then scattering off each other. And in fact, we have a very, very beautiful picture of that. The picture says that two particles will interact by exchanging another particle. Okay? And I'll develop this picture after showing you an example. So imagine that on the left side we have an electron, one coming in from below, one coming in from above. The fundamental picture of how it scatters is that one of them emits a photon. Photons are always described by the Greek symbol gamma. One of them emits it, the other one absorbs it. In the process of emission and absorption, both of them suffer some change of energy and momentum, and that change is the fact that they have scattered. Okay? It's a beautifully simple idea, and not only that, as you know, the photon is a particle of radiation, okay, and radiation is the electromagnetic force, okay, and what do electrons, what property do they have which makes them feel electromagnetism? It's their charge. Okay? So the fact, so Coulomb's law, which you know, two particles of some charge Q1 and Q2 have an attraction or repulsion, it comes from this picture. You won't learn it through this picture. This is a picture in quantum theory. Okay? But the effective result of this picture is Q1, Q2 upon whatever, 4 pi r squared. Okay? So this is the fundamental picture of how objects interact using the electromagnetic force. Now, there are other forces besides the electromagnetic force, and in every case they act by exchange of some force carrier between one particle and another. And one thing which you might want to think about is what is the range of the force? How far, over what kind of distance can one particle exert a force on another? If you look at your own daily experience, there is one force that extends over immensely long ranges. What force is that? Gravity. We can feel the gravity field of the moon. It creates tides. Okay, we feel the gravity field of the earth every time we fall. Okay, so that's immensely long range. The moon, as you know, is very far away, and still we can feel its pull here. So gravity is for sure a long range force. What about electromagnetism? Now here you may think it's not very long range, but there's a very simple reason. You see, electromagnetism acts only, it can be strong only when two objects carry a huge net charge. Okay? For gravity, it's strong when two objects carry a huge mass. There's no shortage of objects carrying a huge mass. The sun carries a huge mass, the earth carries a huge mass. But net charge is very difficult to have because they are both kinds of charge and they tend to cancel. So the net charge of the earth is not very much, if at all, if anything, and the net charge of the moon is not very much. So the electromagnetic force between moon and earth is small, but the electromagnetic force itself is long range. What makes it small is that there isn't much charge in the first place at either end. Okay? In fact, both gravity and electromagnetism obey the inverse square law. I think this is something you might have encountered. Okay? Newton's law of gravity is an inverse square law. Electromagnetism is an inverse square law, and a very simple rule of thumb is any inverse square law is a very long range force. There are some forces which, however, are very short range. Okay. So before that, let me just say, how does the range of the force relate to the mass of the particle carrying the force? Do you know what's the mass of this gamma, this photon? Yeah, what's the value of the mass of a photon? 0 is exactly 0. That's what makes the force infinitely long ranged. Okay? And we expect that the particle which is responsible for gravity, called the graviton, also has mass 0, and it is responsible for gravity being long ranged. But now there are some more particles and some more forces. Okay, so since the photon is massless, the force of electromagnetism is long range. But if there's a short range force, then the carrier of that force must have a mass because the mass limits the range. If the particle has a mass, it's very easy to show by calculation that the force falls off exponentially, not 1 by r squared, not inverse square, but e to the minus r. I don't know if you have ever thought about the function e to the minus r, but that function falls off very, very fast, much faster than 1 by r squared. So now let's take a look at the list of particles and list of forces. Turns out that besides the two that you know about, electromagnetism and gravitation, there are two more forces in nature exactly, and all these four forces are communicated by some fundamental particles that we call force carriers. And out of these forces, two that we have just discussed are long range and the other two are short range. This is a very, very key fact, and here they are. So the four forces are electromagnetism, long range, carried by the photon; weak nuclear force, this is a force that was responsible for radioactivity, and you know we haven't known it for more than about 100 years. Radioactivity is a relatively recent discovery of about 100 years ago, early 20th century, and it's a short range force. If it was a long range force, we'd have discovered it earlier. If you think of it from a historic point of view, the long range forces were found first because they were long range. The short range forces were found only when we could have the technology to probe inside the atom and see them at work. But it turns out there are two of them, one which is weak nuclear and the other which is strong nuclear. So there are two nuclear forces. The strong one is responsible for the fact that these protons and neutrons stick together. First of all, for the fact that quarks bind into protons and neutrons, and then that protons and neutrons stick together and form a nucleus. So anything responsible for binding the nucleus is a strong nuclear force. Things responsible for these occasional emissions of stuff out from the nucleus, radioactivity and similar phenomena, that comes from the weak force. Turns out the weak force has 3 carriers, the strong force has 8 carriers, and if you add up 1 plus 3 plus 8, you get 12 bosons, whose existence we know beyond a shadow of doubt. Okay? The graviton has not directly been seen, so I won't count it for the purpose of this talk. And now you can see that we know 12 bosons, and the Higgs, which I'll introduce in a minute, is the 13th boson. Okay? But what you see from this picture is that the W and Z bosons in particular, conveying a short range force, have to have a mass, and that mass is important so that they don't travel too far and create a long range force, because experiment tells us that the weak nuclear force is not long range. Now I told you that all matter particles are fermions, and another simple fact is that all the force carriers, which I listed on the previous page, are bosons. And bosons have the opposite behavior from fermions. They are highly collective and cooperative in their nature. They like to condense, they like to be together, they like to, if you give them an environment which is sufficiently cool, for example, very, very low temperature, they like to come together. They have no problem for 100 or 1,000 or 1,000,000 bosons all to sit in the same seat. So if you were all bosons, it would be very cheap to make an auditorium for you. You just have to have one seat. Everybody could fit into that. So that's their nature. Now see, this nature of bosons is also extremely useful for the things that they do. Why does a laser work? What is a laser? Okay, won't go into the details. A laser, the reason, you know what a laser looks like, right? It emits some kind of a sharp beam of light, which is nice in movies and discos and public shows and so on, or even these are just some laser pointers. What is it that makes this beam so fine and so sharp? It's just a light beam, but it doesn't look like your torch light beam, right? So what is it different about it? The difference is that all the photons which are coming out are all marching in step. Okay? That means essentially that they behave as if they are all in the same state. They are coherent. The word we use is coherent. But you see, fermions will not be coherent. Fermions refuse to be coherent, but bosons are perfectly willing to be coherent. So you can make a coherent light beam, and a coherent light beam is a laser. And once you managed to make that, because of their coherence, they have extreme intensity. So a laser can damage your eyes, a laser can be used also to damage your eyes to perform laser surgery, or other lasers can be used also in other forms of surgery. Why? Because of the constructive behavior of all the bosons that form the laser beam. So it's important to remember that photons are bosonic or bosons, and in fact all force carriers are bosons like this. So I've given you now, I think, a reasonable survey, and it's time to summarize what we've learned about elementary particles. But before that, one thing which will make you appreciate them a little better is that there are three properties we like to know given any particle. One is what is its mass, which you all know what mass means. Now you see, these things are very light on the scale of grams or kilograms. So we use a unit called giga electron volts. In physics textbooks, you'll find it defined. But it's very simple to think of it this way. A proton is roughly 1 GeV, 0.93 something GeV. So anything else, we'll just think of it in multiples of a proton. So it turns out an electron is about 1 over 2000 the mass of a proton. The particles I'll be talking about, notably the Higgs, turns out to be about 125 or 130 times the mass of a proton. So just to give you a ballpark of what masses can be like for these particles. Of course, they also have electric charge. Again, this charge is measured in coulombs, but I won't bore you with the number in coulombs. We'll just think that the proton's charge is 1, and then everybody else's charge is multiple of that. It could be 0 or 1 or 2 or something. Charges always come in multiple, luckily. And yet another property, this is very, very obscure at first, is that every elementary particle has a possibility to be spinning on its axis with a fixed angular momentum, like a little top, okay? But the difference with the top is that you can take the top and you can speed it up or slow down its spin, but elementary particles, a given particle always spins at exactly the same rate no matter what you do to it. So we say that spin is an internal property. It's not something you can change. Just as you can't change the mass or charge, you can't change its spin. It's created with that spin, and that will be its spin forever. And the spin is measured in units of a particular constant called Planck's constant, and the electron has half a unit of spin. In fact, all fermions have a half integer unit of spin, and all bosons have an integer unit of spin, and this covers all possibilities. So here's the grand summary of what I've told you, and I hope now it's reasonably clear. The first row consists of things we find inside the atom. The second consists of particles that we find elsewhere. The third consists of all the force carriers. And now that I've told you about spin, I'll show you the spin of each of these, and you'll see very, very special about the last column. Everything that we know up to now that makes up matter, all quarks and electrons and so on, have spin a half unit. All the force carriers, except the graviton, have spin 1 unit. But there's a new particle which we now know since 2 weeks, which has no spin at all. This has never been seen. We've never before 2 weeks ago had any elementary particle in our set of particles that had no spin. In fact, we didn't even know if nature would make use of the possibility to have no spin, but now we are reasonably sure. And this no spin particle, spinless particle, is the Higgs boson. Just as I've tried to explain for the rest of the particles, they have a certain class of properties which make their physics what it is. For example, some are fermions, some are bosons. Similarly, some are charged, some are neutral, some are heavy, some are light. We'll see that the Higgs boson comes with a set of properties which make a particular thing, physical thing, possible. And now I'll try to tell you what that is. Now let's, before we get on to what the Higgs boson is, let me ask you a common sense question. How do we actually know the existence of an elementary particle? Sometimes the press makes you feel that a person sitting in a lab starts something, fires up something, they collide, and then suddenly a particle comes out, and oh, this is a new elementary particle. Okay, that's one way. It's not so wrong. Okay, in the early 20th century, that's what often happened. But it became harder and harder to find these because the energy required became higher and higher, And when the energy is high, then you need to build more and more sophisticated machines to find new particles. The question which would arise is, when we build these machines, do we expect what we are going to find, or we just find whatever comes by as if it's a total surprise? Okay? In other words, can we predict the existence of an elementary particle, or can we only be passive bystanders saying, well, now we see electrons, now we see muons, and we make a chart of it, but we have no understanding of why they are. So let's look at history. History is a very good guide to these things. Electrons. When were electrons first found, or who found them? They were found by J.J. Thomson and in fact many others, looking at some kind of vacuum tubes which had some filament which was heated and emitted some kind of rays that are called cathode rays. And the impact, the existence of these was seen in the effect that they produce when they hit a screen. Okay? And if you have seen a cathode ray tube, you might know that just holding a bar magnet nearby, the beam will bend and so on. Have people seen this? Yeah. So that will allow you to infer that there is a particle involved, and that particle, J.J. Thomson proposed there is such a particle, and it got named the electron. Likewise, muons were a complete surprise. They were found in cosmic rays, but really nobody expected them. They are also very much like electrons. However, there are other particles which were predicted first and seen later. This is very, very important, because it gives us a feeling of our participation in the enterprise. It's not just that nature is doing something, but that we can understand the logic which nature is using to function. By understanding that logic, we can first make a prediction. It may not be a sharp prediction, or it might be a sharp one, precise one, and then we can do an experiment saying, well, this is the prediction. The experiment should be focused on looking around that prediction and seeing what is precisely true. And this has happened in three very dramatic cases. This one, the neutrino, was predicted by Pauli in 1930. Do you know why he predicted it? Because in radioactive decay, he found that when you measure the energy that's lost from the nucleus and the energy of the things that are coming out, these two don't balance. There's an imbalance of energy. So he said, well, energy should be conserved. So if there's an imbalance, it means something is coming out which we are not seeing. But look, in 1930 he said this. It was discovered in 1956. So for 26 years, his prediction was there, but nobody had proved it was right. Okay? Once it was proved right, one has to say, fantastic job done by the experimenters who proved it right, but also fantastic job done by Pauli who predicted it. You see, this is the sense in which theory and experiment go hand in hand. One without the other doesn't make sense. With experiment, you can see things, but you can't understand them. With theory, you can try to understand, but you can never be sure that the things you are talking about are there. If in 1956, if neutrinos were not found, people would have to look, they would have said, okay, Pauli was wrong, but they would have had to look for another explanation. You always need an explanation. Luckily, the simplest explanation was true. Here's another example, the positron. This is like an electron, but it carries the opposite electric charge. And Dirac predicted it in 1931 based on mathematical properties of his equation. And very luckily, the following year an experiment was done, and there it was. There was some confusion, but in the end it got sorted out. And here's an example where it was predicted and found within 1 year. There's one more example, the quark itself. Gell-Mann and Neyman, looking at these lumpy protons and neutrons, said, look, there should be something inside them, and that thing should have certain properties which they categorized. And they named them quarks as well. And they predicted them in 64, and certain experiments which probed deep inside the nucleus found them in 68. So these are three examples where a particle was predicted before it was found, and the Higgs particle is yet another example. It was proposed not by Higgs actually, and not by the 5 other people who are named along with Higgs. It was really proposed by Glashow, Salam and Weinberg in 67 and 68. Just to set the picture right, what happened was that in 64, Higgs and many other people found a particular mathematical phenomenon, okay, in which a certain kind of particle, which is therefore called the Higgs particle, produced a certain effect, but they didn't know in what theory this particle should exist. They were not trying to write a theory of nature. They were just saying that a certain effect is produced if a certain type of particle exists. These people said, we are going to actually write down the theory of the electromagnetic weak and strong nuclear interactions, and they didn't probably give it a name, but today it's known as the standard model of particle physics. And in their theory, the W plus, W minus and Z, three bosonic particles of spin 1, were the force carriers of the weak and electromagnetic interactions along with the photon. Okay, and they predicted these in 1973, and they predicted them in 67. Evidence was seen in 73, and the particles themselves came out in all their precision in 1983. So another classic example. And now you see this prediction of Glashow, Salam and Weinberg had a little corollary, and that corollary is the Higgs. Along with the W plus, W minus and Z boson, their theory needed a particle called the Higgs. But there's a difference between why they are needed. The first line, the W plus, minus and Z, are force carriers. I've told you why force carriers are needed. They are needed to communicate the force, in this case the weak nuclear force. But why the Higgs? That's what we'll see next. But look at the time gap. They predicted it in 67. It was found in 2012. I think this is the longest ever in the history of physics, or maybe all of science, I don't know, where as long as nearly a half a century passed between the prediction and the observation. And with the discovery of the Higgs boson, the standard model is complete, and in this sense, we do have a complete and accurate description of natural phenomena in terms of fundamental particles, except for the force of gravity. And you may be puzzled because gravity seems like a very strong force to us. The fact is, it's very strong when large bodies are involved, but the force of gravity between two electrons, it's there, it's absolutely negligible. It's a billion times more negligible than the electric force between two electrons. And this you can even calculate and compare. And so particle physicists generally neglect gravity. However, what I work on and what my colleagues work on has to do with gravity. That would be the subject of a different talk. For today, we'll just take it that the standard model is a complete picture up to present day energies of all fundamental interactions. And the only thing missing from it up till today was the Higgs boson. It was there in the model, in the theory, but it had not been confirmed. Now let's try to understand. Okay, first let's pause for a moment to appreciate this beautiful picture. So here are two particle beams coming in, colliding. They give off fragments of all kinds. The job of detectors is to collect these fragments, reconstruct a picture like this, and try to see whether it corresponds to the production of this, that, or the other particle. And in particular, I'm told that this is an event in which the Higgs boson was produced. Okay, extremely difficult job to find this, let alone to make such beautiful pictures. But here it is. This has now become the iconic picture of the Higgs discovery. And yet I haven't told you anything about the Higgs yet. So you're probably wondering when it will happen, and this is where we start. So now let me talk to you a little about the weak nuclear interaction. You know that all interactions have a force carrier, and that the mass of the force carrier is inversely related to the range of the interaction. And for the weak nuclear interaction, it's pretty clear that the mass has to be of a certain type of value, non-zero and fairly large in GeV, so that the weak nuclear interaction would be sufficiently short range that it's really happening only inside the nucleus of an atom, and we don't see direct evidence of it outside. Of course, we see its products, but we don't see the interaction happening because it's short range. And in fact, here's a picture of what we understand today as beta decay. A neutron below, you know that it's made of three quarks, U, D, D. They propagate, in this picture time goes up, and at some point one of the D quarks turns into a U with the emission of a W. This is a weak interaction. It's a classic signal of a weak interaction. What's the end result on the top left? A U, U, D, that's a proton. But this W splits into an electron and an antineutrino, and there on top you have the three familiar products of a beta decay, a proton, an electron, and an antineutrino. Okay? So this is the model of how the weak interaction works, and it's a very, very accurate model. But the main point is that this W has to have a mass for the interaction to be short range. Also, the force carriers other than gravity all naturally have a spin of 1 unit, 1 in units of h bar. And now there was a problem, and Glashow, Salam, and Weinberg were really the first people to solve it. The problem was that there's a beautiful set of equations for spin 1 particles, but that set of equations requires the particle to be massless. In fact, those equations were extracted from the Maxwell equations, which describe electromagnetism. They are a generalization of that called Yang-Mills equations, but they do require that the particles they describe are massless. Now, that's all very well for photons, which are massless, but it's very bad for the carriers of weak interactions because they can't be massless. And for this reason, during the whole of the 50s and 60s, simply nobody knew what to do. The field was actually stuck. At the time Higgs and others did their work, the field was still stuck, and it remained stuck until 67, 68, when Weinberg actually, I think first, and then the others, had this idea of using this mechanism in a very, very particular way to get mass for the carriers of the weak interactions. So this was the paradox. And they basically said, well, in the literature, there's some work of Higgs and Braut and Engler and Hagen, Guralnik and Kibble, 6 people, all in the same year, 1964. And they said this work suggests a way, a mechanism in which the particle that carries the weak interactions can have a mass defying the second line of this transparency. It can acquire a mass effectively, even though the equations apparently tell us that it has no mass. So they said, let's use that. And the key idea of that mechanism is that a spinless particle can condense. Okay? Now let's recall a couple of things we've said. One is that bosons are particles which don't mind condensing. They have a cooperative behavior. The second thing is, if a particle with spin were to condense, then the whole vacuum, the universe, would acquire an enormous angular momentum. There'd be something wrong with that. But being spinless, it's free to condense. And what condense means is that at every point of space and time, there's some amount of the field of this particle sitting. And this is what I would call the Higgs soup. This is what I had described as a soup earlier. We all live in a soup of Higgs. Okay? And the way this mechanism works is the following. Here's an allowed interaction for scattering of Higgs with a particle, say W particle. But if the Higgs condenses into a soup, then effectively that soup acts as an obstacle to the motion of the W, and that's what we call a mass. This is just a schematic picture to give you an idea. Okay? An allowed interaction is turned into an effective mass for the W particle. I admit that really to explain this, I need to write down all the equations. It's quite technical, it's quite advanced, but this is a very schematic picture that you can take away if you like it. And another even more schematic picture, which I've just told you, is that the mass of the W basically arises because it's propagating through a Higgs soup. So the idea is that we have a particle, that particle condenses in all of space and time, and because of its condensation and its interaction with other particles, those other particles acquire a mass and are obliged not to travel at the speed of light like photons, and therefore they can mediate short range forces. If you have followed me this far, it's not going to get more difficult after this. This is the technical sort of the most central technical fact about the Higgs mechanism, and from now on things will become quite simple. But there's a very beautiful twist which has not been highlighted in the press very much. It's not only the carriers of the weak interactions that get a mass from the Higgs soup. It turns out in the standard model, all the fermions also get a mass from the same Higgs soup. Okay? And here this is something very particular about this. is very reassuring. It tells us that there is one universal thing in nature which endows a mass to everything else. Now let's look how history developed. The W particle was discovered in 1983 and it has a mass of 80 GeV, so it's about 80 times heavier than the proton. And it does carry the weak interaction. So in this sense, the standard model of Glashow, Salam and Weinberg was already confirmed. In fact, they got the Nobel Prize, I think even before 83, around that period, okay? Yeah, much before 83, in the 70s, because these were indirectly confirmed in 73. Soon after that, they got the Nobel Prize. Now, of course, the fermions all have non-zero masses. So, it must be true that the Higgs is there. Now, you see, from a theorist's perspective, it must be true. But from an experimenter's perspective, all right, it's there, but where is it? We haven't seen it directly. We see it through its effect on the soup, but we don't see the particle. And so important is this fact that if we see something indirectly, we must also see it directly so that we can be sure of it, that the entire Large Hadron Collider was built in Geneva with its first and main aim being to detect this particle. And I'll talk to you about that collider in a few seconds. And notice that here theory was not of much help. Theorists said, well, there must be a Higgs particle. What is its mass? We don't know. But people said, well, maybe it's 80 GeV, maybe it's 100, maybe it's 200, maybe it's 500. So you see, there was a lot of uncertainty. There were previous accelerators which looked in the range of 100 GeV, didn't find anything. Okay. Then the Large Hadron Collider came online and started looking, and for a year and a half, it didn't find anything. Then the press started saying, well, it's looking like it's not really there. But you see, if it was not really there, how do you explain lines 1 and 2? Those lines are true. So when something is not there or something is surprisingly absent, you can't just say, well, oh, it's not there, so very good, let's all go and have some tea. That's not what you can do, because something has to be there. Okay? The only answer, if we had not found a Higgs particle, is that something much more complicated is there. Turns out nature doesn't like things which are too complicated. The simplest idea that was proposed in 1967 is simply true. The only thing that happened was it was at a mass range which was very elusive from the point of view of experiment. So the experiment had to be done repeatedly over 2 years in order to pin it down. And now I'll turn to the experiment. So I'm sure you've heard the name of this machine, the Large Hadron Collider. Okay, what is it? Well, it's an accelerator which is basically a tube inside a long tunnel, and the tunnel is really, really long. The tunnel has a circumference of 27 kilometers. It goes underground. I'll show you how it's located on a map in a second. Now, the collider is not an experiment. The collider is an accelerator. Okay? The accelerator is run by people who accelerate particles in it. But then you take those particles and you take them out of, as long as they are in the accelerator, they just go round and round getting more and more energy, and we learn nothing about them. Then you have to take them out and collide them against other particles, and then they produce results, and that's the experiment. That's called the detector. So you should distinguish the accelerator from the detector. Okay? Now, the accelerator and detector together involves not 2,000 plus, I think the correct figure is more like 4,000 or 5,000 physicists from 34 countries. India is an important collaborator. The whole cost of the project was around 50,000 crore rupees, quite a lot of money even for a consortium of countries, including all of Europe, including the United States, India, China, Japan, you name it, all countries with any science, whatever, who give value to science. Okay, now what does it collide? It's a collider. It's called a proton-proton collider because what you accelerate inside the collider are beams of protons. Okay, the reason protons is that they are extremely easy to make. What's a proton? How do you get a proton? Helium. No, hydrogen. Helium has more things. Hydrogen, I mean, I don't know how you actually get protons for this, but hydrogen is actually nothing but a proton and an electron. So if you hit hydrogen hard enough that the electron flies away, you're left with a proton. It's a very simple thing in principle. Okay? And what this does is to accelerate protons to very, very high energies and then collide them. The energy is going to be 7,000 GeV, that is 7,000 times the mass of a proton, rest mass of a proton. So, these protons will have whatever 1 GeV rest mass, and all the rest will be the extra energy they get, their kinetic energy. And there will be two beams of 7,000 GeV each. So, the total when they collide will be 14, 7 plus 7. We haven't reached 14 yet. Up to today, the limit is 8, 4 plus 4. But 14 is expected in the next about 2 or 3 years, after it's shut down for a long time and upgraded and restarted. So, here is the aerial view. If you are actually in a plane, you cannot see these marks. These are made on the map by hand. But you see there are many rings. There's a little ring, then a bigger ring, and then the main accelerator ring. That's because, as I'll show you in a movie just now, the particles are first accelerated in the small ring, then in the bigger ring, then in the biggest ring, and then when they are really energetic, then they collide. By the way, the left half of this picture is France and the right half is Switzerland. So, this is a cross-border collaboration. Even in the days when you needed a visa to cross from one to the other, the particles in the tunnel didn't actually need that. You might be amused to know, however, that CERN, the laboratory, did have a very complicated system. They had to account for every pencil which went from France to Switzerland, even if it went underground. But thankfully, at least in these parts, bureaucracy is on the decline, and now in fact you don't need to account for pencils. This, by the way, you can see Geneva Airport on your extreme right. You see the runway over there. Okay. So, the protons travel inside two pipes because there are two beams, one going clockwise, the other going anti-clockwise, and until we want to use them, we don't want them to collide with each other, otherwise they'll never build up to enough energy. So, there are two separate pipes, one carrying the beam going this way, the other carrying the beam going the other way. Now, there's a very big problem with accelerating charged particles. Do people know what it is? A charged particle, any particle will like to go straight, okay, Newton's law. If you want to bend it, you have to put a magnet which bends it. Because of its electric charge, it bends in a magnetic field. However, if it's too energetic and you try to bend it, it will start to radiate. It will start to radiate light. And when it radiates, obviously it loses energy. It gives off something, so it loses energy. But that's the problem. You're trying to speed it up, give it energy, and it's radiating away and losing energy. In fact, this is one reason why they didn't use electrons. Electrons are even easier than protons to make. But with electrons, this problem becomes critical at these energies. And even with protons, you need such a strong, you need a particular configuration of magnetic fields to make it bend without too much loss. And the high magnetic field would have melted the magnets. In order to have magnets which are not melted, these are the magnets. This long thing, blue thing you see is an example of a magnet, but it's a superconducting magnet. So, it's cooled by liquid helium, and at those temperatures it's able to superconduct, and then it doesn't heat up the way a normal conducting magnet would heat up. So, this is a very key new technology, and by the way, it's this helium which exploded. 1 ton of this leaked about 2 years ago. There was a small breach. The helium came flooding out and a whole ton of it came. Now, imagine liquid helium being released, it just blew up, and it blew up and blew up a lot of that segment of the accelerator, and it had to be shut down. It was a horrible accident, but they fixed it and the thing is working better than ever. Okay. So, now I think the best is for me to show you the movie if it works. Let me just say that there are two, for our purposes, two detectors, CMS and Atlas, which are independent detectors which take the same beams but do their own experiment with different detectors. The idea is you cannot compare the results from LHC to the results from some other accelerator in the world, because there is no other accelerator in the world. It is already expensive enough of this energy. So, in the same accelerator, there are two experimental teams. They do their work separately and they compare their results later. This gives us some confidence that they are right. CMS is the one which has Indian participation. Atlas does not. So in that sense, we are always cheering for CMS. As it turns out, both did equally well about 16 days ago. Okay. Now the quick movie, just take 5 minutes to show you that if it works. But I'm just worried that, okay. So note the tiny ring, a bigger ring, a bigger ring, bigger ring. And this movie was made by the Atlas collaboration. So it shows the particle being accelerated and then going into the detector. So let's watch. So there's the proton, the little red thing. Notice it's getting faster and faster. And now you see one proton goes off that way, one bunch, and the other way. So now they are both going opposite to each other. Now we zoom into the detector, and here are two bunches. They smash into each other. The products come out sideways, and they are captured by the detector, and that's where they are measured. So is it clear how the whole thing is done? Now this machine ran for 2 years, and after that the collision and there was also some shutdown period because of the accident I told you. And then after that the collisions were analyzed, and a new particle was found with a mass of about 126 GeV. That's about 130 to 140 times heavier than a proton. It's not such a shockingly large mass. In fact, what's surprising is that this kind of mass is was within reach even of previous accelerators, but for reasons of trying to gather the data with enough precision and reliability, sorry, they were forced to stop at a slightly lower mass of around 110. So up to 110 had been explored quite well. Moreover, it turns out it's very easy to explore a higher mass range above 160 or 180, because then the Higgs will decay into two W bosons, and that you can see right away. If the Higgs is twice as heavy, W boson is 80. If the Higgs was 160 plus, it would have decayed into two W bosons, and it would have been seen. So it turns out it was simply hiding in the place where it was hardest to see, and it's actually seen by its decay, among other things, into two photons. Higgs going into two photons is an important decay mode, but it's very rare, and it's very hard to distinguish it from all the other things going on in the accelerator. Okay? Because when you collide two protons, people like to say that a proton-proton collision is like colliding two TV sets. A whole mess of stuff comes out. Most of it doesn't correspond to the Higgs. Most of it is nothing new. You have to remove all that from using your computers and your detector apparatus, and only what's left you have to focus on, the part which is clearly new. That's a very, very hard job. Here's the result. These are the graphs provided by CMS above and Atlas below, two different detectors. Do you see, this is the cross section or the rate of events, and horizontal axis is the mass of what is coming out in GeV, which can be used to reconstruct the mass of the particle that was decaying. And you see that around 125, both of these graphs have a very tiny bump. You see the bump? That's the Higgs. That's at least what we think is the Higgs. And here is a very nice photo. On the left is Fabiola Gianotti. She is the spokesperson of the Atlas collaboration. And on the right is Mr. Higgs, Peter Higgs. And you see, this embrace is a very symbolic one for all of physics, I would say, and especially particle physics, because it is really experiment and theory embracing each other. I find this photo particularly nice for that reason. You may also notice that theory is a little bit old and experiment is a lot younger, and that's actually how things are today, because experiment in this field is suddenly blossoming. If you have thought about doing experimental science, it's a great time, because the LHC is still going to run for some years, and who knows what's going to come out of it. So I'm nearing my time limit and I'm almost done. I just need to tell you for 2 minutes what India has really contributed. So we are a part of CMS and ALICE. You might say, what is ALICE? It's not a misspelling of Atlas. ALICE is a different experiment, but it's not looking for the Higgs. It's looking for other things. Okay? So there are other things that the LHC is looking for besides the Higgs. So that part I won't highlight, but we are part of the CMS detector team, and this is the CMS detector itself. It's called compact muon solenoid. I'm not an experimentalist, so I wouldn't be able to tell you too many details, but I can tell you the institutions, TIFR in Bombay and BARC, both here, Punjab University in Chandigarh, Delhi University, Vidyavihar, that is Shantiniketan, NICER, which is a new institution in Bhubaneswar, and the Saha Institute of Nuclear Physics in Calcutta. So all India kind of participation. The contributions have been right from the planning stage. So when this accelerator was proposed, India was part of the group discussing how it should be made, how it should be designed and so on, and what they can contribute. And hardware means actually physically pieces of this big thing, and software, you know what that is. Grid computing, which is a new type of distributed computing, which is needed for the enormous amount of data this thing generates, and of course the all important data analysis. By the way, you should realize that the announcement 2 weeks ago would have come after a very intensive period of analyzing the data. It's not that the LHC or the CMS gives a beep and there's a big sign saying Higgs. You have to actually take a mess of things, analyze them to death, and only at the end you actually can see something that's a signal. Okay. So one of the things that TIFR and Punjab University actually fabricated here in Bombay actually and shipped it to Geneva is the outer hadron calorimeter. So that's one of the shells of this CMS solenoid where the decay products are captured. So it's part of the outer region of that. The other one is called the silicon strip pre-shower detector. If you look in this diagram, you see pre-shower written somewhere on the top right, and you see an arrow to a little green thing. That's the pre-shower detector, and that actually takes out some of the spurious events and gives a better accuracy to studying Higgs to photon decays, which is exactly the decays which have been used to find the Higgs. And in this, this was done by BRC and Delhi University collaboration. I won't tell you more about that. If you want, you can always get a person who was actually involved in the experiment. There are many at TIFR, and they can come and talk to some of you who are especially interested. So now I'm done. Question is it over? Is particle physics finished now? So not really. First of all, the LHC has a lot more to do. It can probe elementary particles with energies of a few TeV because that's its own energy, and that's a few thousand times the mass of the proton. And we believe it could find new particles besides the Higgs boson. And for this, I've given you a little diagram to make you realize the extent of our knowledge and our tested theories. You see, the horizontal axis is a scale of energies where 1 GeV is the proton mass. And it's in this region that we have theories which are understood and tested by experiment. What do we know about the region just beyond 1000 GeV? Not very much. We've never had an accelerator to look there, but we have some ideas, theoretical ideas, what we may find. What do we know about higher and higher energies? More and more of nothing. Okay? Why have I drawn the graph in this way? Because 10 to the 3 GeV, you can't see it, that's the LHC scale that I've explained to you. But 10 to the 19 GeV is the scale of the force of gravitation. That means the force of gravitation has an intrinsic scale. It's not the mass of the graviton, it's a scale associated to that force. And we believe that scale is very important in the ultimate structure of the theory, and therefore to know everything, we should know the entire range, and we've just begun to explore it. So the best that theory can do right now is to suggest a few things that might occur in that single question mark. We are totally at a loss when it comes to things that might happen in the rest of that scale. Now, I don't want to go on too long, but it's just about an hour since I started. But let me just talk to you about one prediction, because we've just confirmed one prediction of Higgs that was made in 60s. Now I want to talk to you about a prediction that's been made in the last 10 or 15 years, and it might be confirmed or it might not in the future. Notice that the W boson and Higgs masses are very comparable on a scale of magnitude, they are about 100 GeV. In fact, all the particles of the standard model are lighter than 200 GeV. But there's a puzzle, it's another theoretical puzzle like the one leading to the Higgs. This puzzle says that whenever you include gravity in theory, spinless particles naturally have a mass 10 raised to 19 GeV, which is the scale of gravity. Gravity takes any spinless particle and pulls its mass to be such a high value. 10 to the 19 is a gigantic number, and it's not the right mass of the Higgs. We know the mass of the Higgs, it's 125 GeV, not 10 to the 19 GeV. So this problem is called the hierarchy problem. It says that there's a hierarchy of masses. The heavy mass is very, very heavy, but the Higgs mass is nowhere there. The Higgs mass is right at energies which we understand. So why? And for this, a new idea has been proposed, and this idea is called supersymmetry, SUSY. And this is the observation that such a problem can be solved only if there's a new set of particles in nature that are called superpartners. That is, there's one for every existing particle, there's a superpartner, and this shows you above this sheet are the known particles, and there's supposedly a whole world of new particles which simply doubles the set of particles we already know. Now, the reason to do this is that if we have such a structure, then this effect of gravity to make the Higgs mass super heavy gets cancelled out between the particles and their superpartners. So it's a kind of symmetry which tries to cancel out the problem. Again, it's very hard to explain without going into the equations. But let me just say that supersymmetry cannot be exact, because if it were exact, then the electron, which is a fermion, would have a bosonic partner, and we would have seen it, would have the same mass, the same charge, and just differ by half a unit of spin, and we'd have seen it, but we haven't seen it. Luckily, we don't mind if supersymmetry is just approximate rather than exact. And in this procedure, in this proposal, every known boson will have a fermion partner and vice versa, but the masses will be split by about 1000 GeV, which is precisely the LHC energy scale. And this brings us to the secondary purpose of the LHC, which is to look for supersymmetry at energies of the order of 1000 GeV. And this is what it will be doing for the next few years. So we have these strange names for the new particles. The red particles are not yet known. For quarks, we have squarks. For electrons, we have selectrons. And for photons, we have photinos. The notation is a little inconsistent. The important thing is that the particles on the left have masses below 200 GeV, and the particles on the right are proposed by theory, and they should have masses above 500 GeV. That means that they are just round the corner potentially of being observed in the next 2 or 3 years. Okay? Of course, they may not be. Of course, theory may not always predict something correct. This is one case where a lot of people feel the prediction is very dicey. A lot of people are betting that supersymmetry is not really there. But you know, you can bet all you like. Finally, in 3 or 4 years, we should know. And such particles, if they are found, may also solve what is called the dark matter problem, which you might have also read about, which is the statement that the matter we observe in the universe, that which we can actually see because of the light it emits, is only a small fraction of all the matter in the universe. We know this because of the gravitational effect of all this other matter. And dark matter, if it's there, must be made of some new particles that have some new interactions. They shouldn't emit radiation, and they should be densely scattered. This is like another kind of soup, a little different from the Higgs soup. There's also a dark matter soup in the universe, and we don't know what it is, but it's possible that dark matter is nothing but supersymmetric particles. If that is so, then not one but 2 major theoretical problems could get solved by the same experimental discovery. And in particular, people say that the lightest supersymmetric particle, or LSP, is a prime candidate to make up dark matter. And so if you read about LSP in the next 2 or 3 years, you'll know that another prediction of theory has come true. Okay. Now, a little thing addressed to students here. I want you to think about who will have the next great idea. Okay. Are we going to sit here and wait for somebody somewhere to have the next great idea, or are we in India going to be a part of this? So I want to just emphasize to you, of course, these obvious things. Particle physics has a very bright future. A lot of key questions remain to be answered. We have both theoretical and experimental labs in India which can answer them. And I want you to think a little bit about the people who've already done fundamental work in science in India. Who is this? Very good. Who's this? This is not Bose. Chandrasekhar. Very good. Who is that? This is Salam, and a lot of people don't think he's Indian, but he was born in undivided India, in the Indian subcontinent. In fact, in the same place as Hargobind Khurana, who I don't think I have here, but Khurana migrated to the US, Salam migrated to England, but for some reason we consider Khurana was Indian and Salam was not. Well, anyway, it hardly matters. He was from Punjab, whether you like it or not. Bose, Satyen Bose, and Homi Bhabha. And who's going to be in the last spot? I hope one of you. I'd be happy to give a lecture 20 years from now in the same place, and I'd be happy that one of you has your photograph in there. And with that, I'm done. So thank you very much.